Hello. Today I'd like to talk about modeling feedback through the use of an unstable system and making it stable. My project was done through a ball and beam example that I had used in another course. Brief introduction. Feedback goes back to the Romans. They used water to control certain devices and were able to be one of the first civilizations that used it. One of the more recent example was the Watts governor, which was used but not really understood until people started modeling feedback and discovering what actually happened in the mathematics between feedback and the system. Brief overview of how the model came about is shown here. The model of the ball and beam system has both rotational motion and translational motion. Through the set of equations, which are hard to see, you can see from the diagram that as the angle increases, the ball rolls faster. And likewise, as it decreases to 0, the ball could possibly stay still. Using those equations and summing around the forces, you can see that the ball mass, gravity, and the angle that it makes with the x-axis is basically all that is included. Next, use the Lagrangian dynamics to solve the system again and get a set of equations for it. Through the equation 9, you can see that it depends on Q and Q dot. And by alternating those in the system, you can see that 10 is the partial derivatives and makes it a time derivative equation. 11 and 12 become the final equations where your linear acceleration is related to your angular acceleration and all the terms that follow: the angular velocity, the angle, linear velocity, and linear position. By using these equations, one input into the other, in initial conditions, velocity being 0, the board has to be level. Using the previous model, it's better to try to work with it in state space form. State space is also called Euler's order reduction, where the model can be shown as a series of first order differential equations, which it makes it more manageable and more attractive to solve. As you can see, the model has been broken up into an x vector, or x dot vector, x1, x2, x3, x4, and the resulting terms that go with those equations. So you have your position, your linear velocity, your linear acceleration, your angular velocity, and angular acceleration. And they depend on where x2 is your velocity, x4 is your angular velocity. And for this, we also need an input, and we assume that the input is a angular acceleration. The output to this equation is through MATLAB and Sage. You can see that they're both the same for the equations. On the bottom, these are the equilibrium points, and you can see that x3 is the only dependent equilibrium point, and it also depends on 2 arbitrary constants. Linearize the model to make it more manageable and come up with a new model that is similar to the system. Here you can see that it has been greatly reduced from the previous. Even the input has been drastically reduced. Looking at the solutions to the linearized model, it's strikingly similar to the first. You can see the linear velocity, the position, and the stage output are both the same. From the previous model, the angular acceleration is reduced further to allow for a constant angular velocity. The state space diagram reduces to a series of first order equations like the original did. Using numerical methods in MATLAB, I was able to solve this system again. This is ODE 4.5 and ODE 2.3, which are ways of solving nonlinear differential equations in MATLAB. From here you can see that the position, the angle, the velocity, they all over time are the same as and looking again, you can see that the equilibrium is the same as it was before, dependent on two arbitrary constants and x3, which is the angle of the board. Next, we look at the Jacobian for the system. This is the Jacobian for the full system, and as you can see, it's pretty messy, but it reduces down to a simple x1 or just this not very interesting system. Looking at the eigenvalues, they're all 0. There's nothing known. The previous model is very difficult to work with and almost impossible to solve. So we work around it. And to do this, we make some assumptions. The first assumption is the angular velocity is constant. Then the angular acceleration is 0. Second assumption is the angle of rotation is so small that the sine of the angle is equal to the angle itself. The state space form again with the input, it's the linearized version. The equilibrium points are exactly the same. The Jacobian is exactly the same, and therefore the eigenvalues are exactly the same. Even plotting the response is exactly the same. Unstable all the time. There's nothing that can say. But it is possible to make it stable. The method of making it stable is by a feedback system. Here's the make the stable system, or I want to show that you can make the stable system. Just make a stable system. To this, we're going to use the Laplace transform. It makes it easier because your convolutions that you would have to do will now be just multiplications. So as you can see here, x of t will go to some x of s by the formula, the integral from negative infinity to infinity of some function of t multiplied e to the negative st dt. These have been used lots through control systems and are. This system at the bottom is actually using the linearized version, and it becomes a fourth order system. But it can be reduced further to a second order system where x of s depends on some s squared. Another way to look at it is through the state space form. We briefly looked at that before, where ax plus bu is some response of the system. Well, we also want to add some using the step response in MATLAB, which is just some response of the system to a basic u. We can see that our second order Laplace transform equation gives the same output response. Here we'd like to apply feedback. Feedback can be used to control the system by some parameter. The stability in the system depends on the ball being in the center, the board angle equal to 0, and the angular acceleration and velocity equal to 0. This on the general system will be stable, and it's the only time it will be stable, because if you move the angle at all, the ball is going to roll. And you have no way of controlling how the ball is going to move back the other way. Using the standard model for unity feedback, you have this T of s is equal to G of s over 1 plus G of s. Applying that to our equation, we gain a second order equation. It's no longer something over s squared. It's s squared minus some other constant. The step response of this system, as you can see, is now oscillatory. And it'll be oscillatory for all functions. It's not stable, but anywhere you start the ball, it's going to oscillate around the position. Comparing this to the previous one, it's a much more interesting system. One question to be asked is, can this be made better? This can be made better by adding a controller. A controller helps increase the stability by changing the poles in the S domain, which equates to the eigenvalues of the function, except for S is equal to some real number plus imaginary. Without going into that any further, and still using Laplace transform, I'd like to apply just a standard proportional and differential controller, which, as you can see, the form here is some Kp, which is just some value, times the angle, plus Kd times the derivative of the angle. And then in Laplace form is right next to it. It's Kp theta sub s plus Kd s theta sub s. Simulating the response with the controller as we did before, as you can see, these functions are now stable. The big difference you have here now is you have some overshoot with, depending on the value of Kp and Kd, but your system goes from being always unstable to always stable. Using methods in MATLAB and control system design, we were able to make a stable system. A summary of what we did: by using feedback stability in the system can be created. Controllers help with the stability. MATLAB is useful in designing such devices because the complexities involved are very, very complex. The equations to solve these systems are very complex, and therefore you would need a very, very advanced program in order to do it. And that would be the next step in this, is writing a very advanced simulation program that can take in all the parameters and solve the system for you. I'd like to thank you for listening.